Okay, so very good evening and welcome to this channel, Physics for Students, and we are continuing our lesson in terms of understanding the concept of topology. What is topology? What are things all about? We started with a very introductory lesson. So Myra Rahat, yes, hi, and welcome to this topology class. So what we did yesterday was that we understood what is actually the need for topology. So I would just like to quickly go through what was covered earlier, then we will start with today's lesson. So we understood that we need a topology in order to understand the evolution of a system, how things go ahead from one place to another. We got to understand that there is a need for generalization. So we went through computers and other analogies to understand. We also understood that the need for a topology is something similar to generalization of Maxwell's equation, etc. We also got to know that how things can be turned from a torus to any kind of a shape, and the basic idea was that to get something which is topologically equivalent and get, most importantly, that what is called a metric independent system without the notion of distance, without any shape or any specific size, how we can make a system so that it becomes very flexible for all of us to understand. We also came to know that to get a metric free system, yet we need something which is called where the measurements will be invariant. That means without the notion of distance, we need to know the concepts of continuity, divergence, compactness, etc. And I showed through the my example of Jamboard that in case that we are looking for to move from one system to other, how things really happen. So just let me quickly share my Jamboard screen where I showed this one. I hope you can see this now. And in order to know things which are very local, we need something which is called a differential geometry. But in order to know things which are more on a global scale, we need a global topology. So distance means basically a specific coordinate system, and we want to move out from the concept of distance, points, etc. So if I say point A is very much close to point C, or point C as a neighborhood, something like that, that becomes more much better, because this is what we called is the abstract space. So that is basically what we learned yesterday, and we also learned that how from Euclidean space to non-Euclidean, from specific shapes to irregular shapes, and from Euclidean to topological space, how do we move about. So from all those learnings, what I would like to talk about today is that what do we actually mean is a topology, because topology itself will require certain definitions. Now here comes the first and foremost difficulty is that, yeah, Vishnu, hello, good evening. So the most important things which comes in this learning is that when we are learning topology, we are going to define everything in a very new way, in a way where which is not a metric system, which is not a space, which is neither a coordinate system, something very weird. So you see the hassle or the problem starts, number one, that we need to define things on a very microscopic level. What is a point? What is a line? What is a space? Most importantly, all these things needs to be defined. Now, why do we need those definitions? Because those definitions, which were there maybe 1,000 or 2,000 years for those times, that won't be applicable, because we are moving into a new world, into a new set of systems, theorems, axioms, and definitions. That is the first most important thing. Yeah, Praveen, very good evening. Namaste. So we need to welcome to this topology second class. So we need to define all those things. So first thing, that is the basic challenge, that how do we define those things? So the task starts first of all in defining certain points, axioms, theorems. Point number one. Second thing is that when we are defining those things, we are not being able to use the usual mathematics, but we use set theory. I will come to that why we are doing set theory. So when we are learning topology, remember that the increasing number of difficulties or the problems is not with the mathematics, not with the concept of abstract things, but basically that you have to start right from zero. That means you have to define what is a point, what is a line, what is a shape, what is a space, Everything needs to be redefined. Yeah, Maida, very good evening. So all those things, once they needs to be redefined, that's require a huge amount of task. So here is the definition. What do we mean by topology? So we call the Greek word, which is topo, which means place or local, and logy obviously means study. So that means topology is a study of properties of spaces that does not change, even the distorted, wrapped, or twisted. Now, you might be asking a question that the next line states that topology studies properties of space that are invariant under any continuous deformation. That is also true. And a study that is measured with shapes and sizes that remain same when they are distorted. Now, the basic question is, which comes, is that why do we need this distortion? Okay, let me go to my Jamboard so that I can explain things in a better fashion. So in case that we need a kind of a regular polygon, say for example, if I take this kind of a shape, or maybe I take kind of a this kind of a shape. Okay, now when I distort it, distort means I bend, twist, or whatever the way I do. So first I would say I start with this particular part. I start with a sphere. Okay, and I try to distort it in a kind of a torus like this. Okay, and I then start with this kind of a thing, and I maybe make any distorted object, something like this. Okay, so now the concept is that if this is a kind of a torus, say for example, okay, let me take a torus from the internet. That I think that looks better because my handwriting is all not that good, right? So I will try to take a torus and put over here so that this looks much better. So let me remove this one and let me copy and paste this part of the torus. It's taking a little bit time from the internet to copy. Yeah. So yes. So okay, this is the erased part, right? Okay, so when I try to, distort it in the form of a torus, this circle, let us assume that there is no hole. It is a kind of a torus with no hole, some kind of a thing. It can be something like that. Now the concept is that all of those things which I'm trying to make it as a torus, or I'm giving it this kind of a shape. Now, why I'm doing all those things? The question is that why I am distorting objects. This is the first thing that we need to understand. Why I am distorting these objects. Okay, so the basic reason is that whenever we try to distort this kind of a thing or this kind of a thing, or maybe even I can take a triangle. I can take a triangle and I distort it to some other shape. Now, the reason that I am distorting all these objects into a different kind of a shape, etc., is that we want to take one single, I would say, property. Let me put it as that one single collection of objects, that possess a certain property. Okay, let me make it a little bit smaller, put it up here, it looks better. So one single object that possesses a certain property. That means any kind of a shape which I'm doing, say for example this shape, or I take up this kind of a shape, or if I take this kind of a shape or this kind of a shape, any shape, if I distort it, then what will happen is that the question is that if I distort that, then can I bring back from this space to this space, or can I bring back this back to this, or can I bring back this back to this? That means if I do this deformation with a function called f, and then I can bring it back, that means the inverse of that function is also true, f inverse. So if it goes from here to here, then coming back from here to here, if the inverse function is also true, that means what happens is that I am getting things on a very lumped up manner, and I can get back to the original thing. You can think of this part of the understanding, something which is called a space-time continuum. If I've got a space separate and I've got a time separate, then if I merge it together into a kind of a lump sum, which is called a space time, then the mathematics becomes easier. That means in order to measure the angles of a particular polygon, say for example this, or for example this, or the lines are there, I can make a similar kind of a different kind of a shape where all those measurements are reduced. As I told you that we always in terms of topology think that we are trying to reduce mobile phones several purposes, smart TV several purposes. So if I get this kind of a shape, or I get this kind of a shape, then I really don't have to measure those angles, etc., maybe the lines, distances, etc. But you see, one thing becomes very interesting is that some property will remain invariant. And if we can design a mathematical tool which will discover or measure those mathematical properties which are invariant, we are done. That means for an isosceles triangle or a rectangle or for a square, all those angles, measurements, perpendiculars are not required. That means what we are doing from a regular polygon, we are moving to a abstract kind of an object where things are becoming much easier. That means a perimeter or a circle or the area of the circle, volume, etc. of a sphere, all those things are not required. Why it is not required? Because if I create this kind of a shape, as I told you here, that a one single collection that possesses a certain property. So if this shape has kind of a property, okay, which matches with this one and this one and this one, say for example, then if I study the property of this shape, I can understand what this and this is. I hope I can make things clear. Are you all getting Praveen and Myra? Are you getting my point? I'm going back. I will go to the mathematics of topology a little bit later. But first of all, I want to show you the basic idea. So that means the measurement of a circle, the measurement of a square, the measurement of a triangle, the measurement of this kind of a shape, if all of them are reduced to, say for example, this kind of a single shape, please do let me know. Please do send some comments also so that I can understand you're getting my point or not. If all these shapes with their properties are reduced to a single kind of a shape, like this one to this one, this one to this one, this one to this one, then what happens is that we get a single object possessing all the properties of a polygon. All the properties of a polygon. That means it becomes easier for all of us to understand that in order to measure, say for example, this part, then the angles, then this angle, then this line distance, whether this one is parallel to each other, this line is parallel to each other, all of them are now reduced to one single object. And if you study the properties, that is why it is important, properties of these objects, then things will become easier. So that is the essence of a topological object. We call it as a topological object because we will see when we learn algebraic topology, that is the basic understanding. Get a kind of an abstract shape, assign those properties regularly from the polygons, and see, most importantly, here I have missed one part. Most importantly, you have to see that if these objects can be defined into these objects using a kind of a function called f, then I have to get back this property back to this to this, this to this, and this to this. And I have to get a inverse of f also true. And then I called this to be, technically I call it as homeomorphic. Homeomorphic. Right? So that is what. And in case of a homeomorphism, the smooth functions and its inverse functions maps from one place to the other. All shapes will be, no, all, I'm sorry, all shapes won't be the same, But yes, I mean to say, yeah. I mean, so I can understand mind of what you're trying to tell. So all shapes won't be the same, but they would have a similar kind of a property. So if instead of studying so many shapes, if I can reduce all those, say for example, I've got 10 bottles of different sizes and shapes. Now, if I reduce all those 10 bottles, Maida, to one single structure, then what happens? Things again become compact, easy to understand. And then I will see that from that single abstract bottle, can I get back to all those bottles, etc. or not? If I can get back to all of this, then that is easier and through a smooth function. Yeah, that is the essence. Okay. So that is basically the idea of what we call is a topology. That means I can twist it, I can bend it, I can distort it, but the properties of the space will be invariant. Now, what is that property of a space? That is the basically the thing that we are going to look over to it. So here you see the the rectangle can be turned into a circle or maybe a sphere, like a cup of donut is similar in topology. Absolutely right. Absolutely right. So that is how, right, Praveen, you're absolutely right. But this one, what I called a circle or a sphere, say for example circle, it cannot be made into this infinity sign. Okay. So but you see that what Praveen has just now told, it is right in front of all of you. The cup with a function, it is straight away turned into a donut, and the donut straight away turned into a cup. Now you see there is a similarity between the donut and the cup, is that both of them has got a hole, and technically we call it as a genus. We will come to that part later. So these are actually few of the topological objects that we do. Now why we call them as topological objects, or I mean to say, what are the features? We will come to that later. Klein bottle, Mobius strip, ball, donut, all those things, they are basically called topological objects. And we also see from here that here it is the same thing. I mean, geometrically, they are the same thing. I covered this part, etc. Now, apart from this, when we have learned what is the topology, what actually is the basic purpose of topology, we also need to understand what is the importance of topology. Now, most of the students, they actually ignore this part. The reason is that you have to study, you have to score a good marks, etc. But why are you studying? I mean to say, for example, in terms of career, in terms of your understanding, why it will carry a difference, or why it will carry a change, that is also very important. So I would like to quickly give through importance of topology. So here you see that all these Euclidean polygons, etc., are getting deformed. Despite this deformation, some properties remain invariant. So what you read the bottom of the last two lines, generalization helps to extend the properties of Euclidean geometry to various other spheres of mathematics. Now here, most of the students, they ignore one part, that if you learn topology in a very good way, in a very good fashion, I'm going to say with the real importance, then there is one thing which is becoming, which will be a kind of a blessing. You will learn one thing very in a very good manner. Can anybody put up in the chat box? I mean to say, if you learn topology, apart from scoring good marks or your career, etc., there is one thing which is going to be very important for you. I mean to say, you will get a benefit out of that. Can you tell what it is? First thing is that you will learn how to write a proof-driven mathematical theorem. I assume that you know a little bit of real analysis before you come to topology. First is that you are going to learn a very good proof-based mathematical system. Point number one. The second thing what you are going to learn, which only I emphasize on this point, which only topology can teach you, is that further in your research or study in mathematics, you can develop a proper mathematical system, or a physics. If you're doing a kind of a research, you can develop a full driven mathematical or a full driven system. Now you tell me what is the reason why I told you that you need to only topology can make you teach this, because as you see that I have told, the topology helps you to define everything right from point zero. This is my nose, this is my head. These are two my ears, this is my lips, this is my chest. Everything you have to define, and you have to show and prove that why this is my head and this is my nose, because you are moving away from the metric system. Exactly the same thing you do in kind of a new research, either it is physics or it is mathematics. Because when you're doing a new theory, for example, let us imagine when Einstein was discovering special relativity or any kind of a discovery, Copernicus, Galileo, things are totally unknown. You are teaching to the community, you are teaching to the scientific community that this is my theory, you need to listen to this theory, and these are the assumptions, and that is how I define. A little bit of real analysis also does so, but topology is one of the best, I would say, subject which will teach you in future, mark my word, to teach you how to develop a research, how to do a research, and how to develop a mathematical system. Because in all other systems, starting from differential calculus, partial differential, thermodynamics, uh, any kind of a system that you see, all things are already defined. Calculus, thermodynamics, trigonometry, linear algebra, differential geometry, each and everything is already defined, but is only in topology and some part of real analysis that you have to say, come on, this is a point. And what do I mean by point? This is the definition. And the definition cannot be circular, because otherwise you will fall into the trap. So it has to be a rigid mathematical definition. So remember that topology actually teaches you to do more of research, more of understanding, and how to develop a full proof-based mathematical system. So that is why I have written generalization helps us to extend the properties of Euclidean geometry or some whatever in other branches of mathematics. You can also see here that this is used in physics. It is used in geometry. Digital image processing uses a lot of topological theories, etc. And biology, DNA, robotics, civil engineering, and geographical systems. So what we can say all from here is this part, that it is widespread. It has got a huge scope of research. That means you yourself can do a lot of research in topology. It is very industry friendly because a lot of industries are using topology. I don't have the paper. I remember one, I think I have shown it in one of my videos in topology, where a person has developed a theory on DNA research, where he's using Riemannian geometry and a lot of topology, 200 dimensions, indices, something like that. If you go to my topology playlist, you will find it. I'm sure I've mentioned it twice. And it's a very emerging field of study. Why emerging field of study? Because any branch which gives you a lot of scope to research is definitely a good way to study. If you don't get into something which is already widespread, and those who are already doing research, what will you do? You will take an extraordinary mind and brain to break through something, but topology has not yet got anything into that. Yeah, so research is something very important. Now from here we migrate to a little bit of understanding of what are the branches of topology, because why that branches of topology we need to understand that, then only you will understand that why we have got so many different branches, and maybe in future which branch you can see. So you see this general topology which we are learning right now. This is a widespread topology. Then we have got algebraic topology, we have got differential topology, and geometric topology is divided into another term which is called a low dimension topology. We will take care of the general topology primarily. Now here you see that what I was telling you, the different properties. You see in algebraic topology, it becomes very difficult in topology to distinguish between things. Again, when I'm talking of distinguish between things, you can say a straight line is different from a circle. Yeah, obviously. But for a topologist, both of them are the same. So in terms of topology, when we are bending, twisting, how can we distinguish between things? That becomes difficult. Showing three-dimensional spaces and in four-dimensional spaces become very difficult. Also, in order to we create algebraic objects and numbers. Now, just pay attention in the figure. What I try to show you, say for example, shape 1 is a kind of a shape, any kind of a shape which has a property which is equal to 2, right? And this shape 1 is equal to another shape that I create, which is equal and has got a property 2. And this shape 1 also has a property of 2. So shape 1 equals to become shape 2. But if I create another shape which has got a property of 10, say for example a random number, we cannot tell that shape 1 is equal to shape 2. It is not. So that is why these are then classified into different groups based on their holes and structures. I told you that torus has got one hole, then there are many holes, genus, etc. And algebraic topology helps to classify different shapes, how different a coffee cup and a baseball is. Now here you see again the same question is coming, this one. All these shapes, if I get or classify the different circles that I see all around the world into one shape, and if I come to know that this shape has got this property, then I can immediately understand all the properties of all the circles around the world by just studying one group of circles. And that is what algebraic geometry does. It classifies into different groups based on their shapes, sizes, and structures. And if I can study each one of those structures, I can very well study other things. I hope I can make things clear. Is it okay? I mean to say, are you getting my point? It is a whole new world. It is a whole new understanding. It is a whole new range of mathematics. But what I'm trying to tell all of you are being able to answer. Please tell me yes or no in the chat box. So this is actually the whole idea of what is called the algebraic topology. Okay, so we are distinguishing it and then we are defining it. Now here you see there is differential topology, which deals with topological properties with smooth properties or smooth manifolds. Is 2D shape and is equal to three-dimensional shape? No, it is not a question of dimensions, Vishnu. It is a question of what are the internal properties it is. Two-dimensional shapes won't be equal to three-dimensional shapes, but two-dimensional shapes of different structures would be more or less topologically equivalent. Okay, so differential topology may be defined as a study of those properties of differentiable manifolds which are invariant under diffeomorphism. Diffeomorphism is something which will come later. It's a very easy concept, differential morphism. So that means differential topology deals mostly with the calculus, because we are studying differentiable manifolds. And as you remember, I have already talked about what is a differential manifold and a smooth manifold in the earlier lectures in general relativity, if you remember. And it deals with properties of invariance of smooth manifold that are carried under diffeomorphism. So it looks like Euclidean. Here you see, I will like to show you what is the difference between differential topology and differential geometry. But it immediately comes to your mind, what is the difference? So differential topology actually studies primarily these problems that are inherently global, obviously. And on the right-hand side, you can see studies properties that are local. Donut and coffee cup are same in case of differential topology. Obviously, these are different in differential geometry, and studies manifold which are very much global and studies manifold which are very much local. Right. Then we come to geometric topology. So geometric topology is the study of manifolds and maps between them, particularly embeddings, etc. Embedding in the sense, okay, let me make this part also clear. So if I get a kind of a shape like this, okay, and I want to study this particular shape. So where is this shape? It is in this computer screen. Is this in this kind of a frame? Then we tell that this particular shape is embedded in this shape. It's a kind of an immersion that we'll come to those things later. Anyway, I don't want to confuse on that. So it is a kind of an embedding. That means the circle is just not a circle. It is embedded somewhere here. So that is why we call it as a kind of an embedding structure. So yeah, so that is what. So there are different types of terminologies. Don't get confused onto that. Surgery, cobordism, algebraic invariance, etc. So lower dimensional topology are 2, 3, 4, etc. And high dimensional topology are 5 dimensions, embedding in codimensions, etc. So from here we get to the understanding that what is general topology, and general topology actually is called point set topology, right? And study the basic concept topology. So metric space, topological space, compactness, open balls, disconnected paths, product spaces. I have not also mentioned box topology, coarse topology. All these things actually come into being. So more or less, it is a kind of a very popular thing that we start first with general topology so that we can understand everything and then move into the algebraic topology, which is very specific. Okay. So what we will do is that I'm going to take a pause today, and tomorrow I'm going to show you that this concept of Euclidean space, that we call it as a congruency, right? This angle is congruency. This line is parallel to this line. This is a orthogonal. This is perpendicular, right? Now, how all those things are changing in topology, and how, as I told you, it's a whole new world, and we have to define each and everything. So tomorrow's class would be taking simple Euclidean polygons, showing their congruency properties, and how these congruency properties gets more generalized into topology, and how, not only that, most important is that if this gets generalized, that means it cannot take place in a Euclidean space, number one. It cannot take space into non-Euclidean space, number two, because we are discarding the concept of space at all. Okay, so what is that new space that we need to define in order to take those polygons, deform, bend, twist, and make a kind of a lump of clay, right? It's called a lump of clay, because that lump of clay, yeah, Shabir, very good evening. That lump of clay, remember, is something very unique. If we study that lump of clay, we will be able to define all the other objects which are a smooth function, which a function and its inverse. We can calculate that. So tomorrow we will look into the congruency part and how these things gets generalized from Euclidean polygons to others, and most importantly, how we can move out from a space. And we need a space, but what is that space and how we can call that space, that we will be coming up tomorrow. So request to all of you, can you just tell me how things are going? Are you really enjoying the classes, or is it boring, too difficult? I will wait for your reactions. Okay, you have started reading Geometry Illuminated. Very good, very good. Yeah, that is a very good book. It's a very good book. And what about others? I mean to say, those who are watching this lecture, are you enjoying? How are you liking? Is it okay, or you need some more time? Okay, it's exciting. Okay. And any reactions from others? How do you find it? You can just speak out. You can just tell anything, because it's just a kind of an interaction that I want to do with all of you. Do you want to know more about? Okay, yeah, Ottawa. Yeah, hi. Winter has set in, I suppose. Thank you from joining from Ottawa. Okay, congruence of modular system is topologically connected. Yeah, in some sense it is, but this congruency, I will tell you how things are going on. Okay, this is very good. So Aparijita, how are you finding? I went through your long comment in the video. Thank you for that. So I think that it is more or less going good, and I should continue with this more often, not always on topology, otherwise things will become very, yes, enjoying is eagerly waiting. Who is this? Okay, Praveen is telling, eagerly waiting for 9:15 p.m. Great, wonderful. So just to tell you one more thing, that Rachid R. Okay. So Rachid, are you from India or you're joining from somewhere else? So the thing is that now, if we are going with topology, you remember I have left forward that tensor part and I haven't touched about that. Okay, Vishak Dutt. Vishak, you are from IIT Chennai. So you went to that my channel of mine also a few hours back. So how are you enjoying? I mean to say, am I being able to contribute sufficiently, which the textbooks cannot? Is my teaching or the way of explanation good? Because you're from IIT, I think you will be able to tell. Okay, you're joining from Canada. Okay, your name is Rachid R. Okay, maybe I'm pronouncing wrong. So Vishak, I need your opinion, because you read a lot of books from IIT and others. So, and also to Rachid and others, that I'm trying to give a kind of a different approach, which textbooks generally don't give, a kind of a deep understanding about the concept. So now the thing is that I need to create a routine, otherwise everything is going wrong. I have left apart tensors. Tensors are not touched for almost a week. General relativity is gone for a toss. I've not been able to do. Also, quantum field theory, since I think 15 days, I have not been able to do anything. So I need to create a routine, and we need to follow that. Do you all agree that Monday, tensors, Tuesday, topology, Wednesday, complex analysis, Thursday, maybe special relativity, Friday, a little bit rest, and then back on Saturdays and Sundays. Do you all agree that our routine will do, or just at random anything comes up? But I think I should maintain a routine because I am making up quite a good notes on tensor calculus, chapter by chapter. I think that if you watch those lectures, your classes and understanding of tensors will be much. I won't be doing exercises just like a tutor. I mean to say problem one, problem two, but I think that good amount of study would be good because the fundamental concepts needs to be clear. Mathematics, I think you can do, or you can send it to me also. I can solve maybe later. Okay, anyway, so no reactions from anyone else. So I think that things are going quite okay. Yeah, so Shabir is saying that it's a systematic way. Yeah, I think I will be able to make it by January, first New Year, because I've got a quite a good surprise coming on, possibly on 16, to get a person whose name is in the Wikipedia, and he has agreed to come on a podcast. It's a very interesting thing. Perhaps the most knowledgeable person, I mean to say, till now, which I have hosted. You can find his name in Wikipedia. So Wikipedia doesn't host anybody's name. Anyway, I will announce it very soon. And I think that yeah, Vaishak, right. So I think that on the 31st, the last day of the year, I can host free webinar on Einstein's relativity. I really don't. Yes, sir. I think first topic should be great. Yeah. So I don't really know, because you people might be busy attending to parties at the before the midnight strikes and the on the new year comes in. But I think that we can go to the party after attending Einstein's general relativity, which is equally fascinating. So I think, let me see. I really don't know how will I be able to do. So 31st of December, I think 8 to 10 o'clock or something like that, I can make a free webinar on Einstein's relativity. I don't know how many of you will be joining, because that's the party time, I understand. But any other day, 25th is a Sunday, I think. But again, 25th, people will be busy in Christmas. Lucy Mishra, sorry, sir, I'm late. Good evening. Yeah. So Lucy, can you tell me a little bit about your background? I mean to say, where are you joining from? And no, don't wish me, Amira, right now. Happy New Year. I'm not dying. I will be coming. Uh, so you can wish me on the 27th or 28th. That would be great. Okay. So Lucy, from where from you're joining? Because I have never talked to you. I try to connect with each and every subscribers. So if you can tell me, are you from India? What is your background in mathematics? So we are continuing with topology, right? So, and this is going to be a very exciting time. So anyway, so Lucy keeps quiet. He wishes me yeah, so that's it. So anyway, so let us be back tomorrow at around 9:15 p.m. to see how congruence and other things gets expanded. We continue our learning with topology and general relativity and real analysis and complex analysis and special relativity and tensors and many other things. Oh, what is my profession? Okay, we will talk about it later. I'm just a teacher. I try to teach and make things easy for you. May Allah bless you for a healthy and young life. Okay, thank you. Thank you very much for all your wishes. I also wish you a very happy and healthy life. Goodbye. We'll be back tomorrow. Thank you very much. Please do share the video so that people come to know and more people join and more people should get the advantage. I don't think that there are really, I'm not boasting, there are really classes of topology which goes on live and tensors. I have seen mostly videos, etc. So I'm trying to make things a little bit different, and that's it. Anyway, goodbye, take care. We'll be back tomorrow 9:15 p.m. Oh, Lucy, you're joining from Bhubaneswar. Okay, great, wonderful. Yeah, Vishakdat. Yeah, good night, goodbye.